So today we're going to do some derivative applications review. This is, of course, just in preparation for our applications of derivatives unit exam, which is coming up right around the corner. Let's get started. So we're going to get a broad review of applications of derivatives today. I want today to be a you try, I go over type of lesson. This is because everything that we've covered, or everything rather that's in this video is stuff that we've covered before. And I want to see if you guys can test yourself just to make sure that you're confident with the concepts that we've learned so far in this unit. Now, just a reminder, the concepts that we've covered in this unit so far are the first and second derivative tests, optimization problems, vertical, horizontal, and oblique asymptotes, curve sketching, which kind of goes in with all of the above, sort of, although not really optimization so much, displacement, velocity, acceleration problems, as well as rates of change of area, volume, and then the most recent one, triangles. We're not going to be able to hit all of these concepts today. That would be quite a long lesson if we did. So I'm just going to kind of pick and choose some of these concepts here. Once again, though, I want you guys to try these questions, and then we'll watch as I go over. Anyway, here we go. First question. Find the intervals of increase and decrease, as well as the concavity intervals for f of x equals 2x cubed minus 4x squared minus 8x plus 3. Pause the video here. Give this one a try. Okay, so I'm going to go over this one now. When we talk about intervals of increase and decrease, what we're really talking about are the areas where our derivative is positive and where our derivative is negative. Just keep in mind, the derivative of a function tells you the rate of change of that function at that point x, right? So if you have a positive rate of change, that means the function is increasing. And if you have a negative rate of change, that means it's decreasing. So we'll worry about that first. We'll worry about concavity afterwards. We'll worry about intervals of increase and decrease here first. So start by taking the derivative of this. The derivative of f of x is going to be 6x squared minus, this 2 comes down, 8x, and then the derivative of minus 8x is just minus 8, and then the derivative of 3 is just nothing. So it's 6x squared minus 8x minus 8. Okay, so we want to find where this is positive and where this is negative. In order to do that, we have to find the zeros of the function first, because those are going to serve as critical points for us to test whether it's positive or negative within there, right? Notice this is a quadratic at this point, like the derivative is a quadratic. I did this question on purpose that way because I wanted it to be a quadratic, because then at least we can solve for where it's equal to 0. You can tackle this in one of many ways. You could use the quadratic formula if you really wanted to, or you could factor it. And I think this one is factorable. Let's just see, though, just to be sure. If we factor this, we'd have to use the adapted sum product rule, which says we're looking for two numbers with a sum of -8 and a product of 6 times -8, which is -48, I believe. Yeah, -48 would be the product. So two numbers with a sum of -8 and a product of -48. I think that would be -12 and +4. Just double checking. Yeah, that totally would be it. -12 and +4 will make that work. So since we found the two numbers that make it work, use it to split apart this middle term. So we have 6x squared minus 12x plus 4x minus 8. So again, -12, +4, that gives you this sum and this product. Now that we've split apart that middle term, remember you put brackets around the first two and brackets around the second two. Out of the first two here, we can factor out a 6x. So if we take out 6x from that, we got 6x times x minus 2. And out of these second two here, we can take out a 4, so it's +4 times x minus 2. And notice that they match up, x minus 2, x minus 2. That tells us that we've done this correctly. So that means the factored form here is 6x plus 4. That's from these two pieces here, multiplied by x minus 2. And that equals 0. Whew. Now that we have this all factored, just look at where each piece is equal to 0. This first piece here, 6x plus 4, if you set that equal to 0, you'd -4 divided by 6. Long story short, you're going to get x is -2/3 as being one of your critical points. As for this other one, that's an easier one to find a critical points to. You just add 2 and you've got x equals +2. Now, what do we do with these? You know, it's all nice that we have these critical points and all, but unfortunately, we also have to test these. So we have to say whether we have an interval of increase and decrease above and below each one of these. So what I do is I set up a table, and I first start by looking at the one that's the smallest. So the smallest number here is -2/3. So I'm going to start by making my table say x is less than -2/3. There we go. And then I have my in between. So between these 2 points, -2/3 is less than x, which is less than 2. That's my in between. And then we have our biggest one, which is going to be bigger than your greatest critical point. So x must be greater than 2. Now, in each of these intervals, you just pick any point. I'm just going to fix this 3 here, kind of looks gross. You just pick any point that satisfies this condition and you plug it back into your derivative expression. Now, the reason we plug it into the derivative is, again, we're looking for where there's an increase or a decrease. An increase means we have a positive derivative. A decrease means we have a negative derivative. So if we pick a number that's less than -2/3, I think one number we could test is x is -1. If you plug -1 into your derivative, you're just going to have to give me a second here. Plug -1 into the derivative, you're going to get, give me 2 seconds here. You're going to get +6. So that equals +6. That tells you we are actually looking at an interval of increase in this interval right here. So this interval is an interval of increase. When you're below -2/3, the function is actually increasing. Now let's pick a point that's between these two critical points. I think the easiest value of x that would work here would be 0. If you plug 0 into your derivative, that one's going to go pretty quick. It's just going to equal -8. Since it's a negative number, that's an interval of decrease. So we have an interval of decrease in this one. Now, even though it wasn't asking for in this question, since we went from an interval of increase to an interval of decrease, we can therefore say with full certainty that x equals -2/3. That point is going to be where we have a local maximum point. So there's going to be like a little hill right at that point right there. The last one here, though, we got to pick an x greater than 2. An obvious answer for that is x is equal to 3. If you plug 3 into the derivative, give me a second here. 6 times 3 squared minus 8 times 3. Oops, 8 times 3 minus 8. That gives you +22. I was expecting it to be a positive number there, just didn't know what the value would be. So +22, either way, it's a positive number. So there's upwards on that one. So that is an interval of increase, which means since we went from downwards to upwards, x equals 2 is actually a local minimum point. So it's like a trough right at that point right there. That's all we had to really do there. Showing this table, showing where our intervals of increase and decrease are, that's really all we're looking for here. That would be enough work to show me the intervals of increase and decrease. Now, we got to find the concavity intervals now. Concavity, however, is not found by the first derivative. Concavity, which tells you like whether it's concave up or concave down, that comes out of the second derivative because it's a change in your rate of change. Second derivative of this function, f double prime, is going to equal the derivative of this guy over here. So it's going to be 12x minus 8. And once again, to test the concavity of this, we have to set this equal to 0. But here's the good news. This one's a lot easier to solve. We don't have to worry about doing factoring because this is only a linear equation. It's not a quadratic. So to solve where this is equal to 0, we just have to add 8 and then divide by 12. If you add 8 and then divide by 12, I'm pretty certain that's going to give us +2/3. So x equals +2/3 is a potential point where we change from concave up to concave down or vice versa. We got to test this one. So once again, even though we only have one point we're testing here, we still have to use interval testing one more time. So let's give it a try. Using interval testing, we're going to say x is less than 2/3. That's going to be our first point that we're going to test. And then we're going to check x is greater than 2/3. So when you only have one critical point, you're testing 2 columns. In this last one, when we had 2 critical points, we had to test 3 columns. So there's a bit of a pattern there. All right, let's test x is less than 2/3. If we test that, let's just plug in x is 0. That makes it nice and easy. Remember, we're plugging this into the second derivative because we're testing for concavity here. If you plug x is 0 in that, you're going to get y is equal to -8. That means since it's a negative number, we are concave down. It's a concave down segment right there. Now let's check a number where x is greater than 2/3. I think an obvious one there would be x is equal to 1. If you plug 1 into this equation, it's just 12 times 1 minus 8. Obviously, that's going to be +4. It's a positive number, though, so we're concave up in that interval. Since all this question was asking for was the intervals of increase and decrease, as well as the concavity intervals, rather than the actual points of inflection, or the local max mins, since it wasn't asking for that and was just asking for the intervals, we can now say we're done. Really, our answers are just what we've shown here, right? So as long as we're just showing our work on that one, full marks all around. Anyway, let's move on to the next question. That one actually took longer than I was expecting, but here we go. Question 2, a company has decided to revolutionize the cylinder bucket market. That's interesting. They want to optimize the buckets so that they still have a volume of 12 liters, but want to use the minimum amount of material. Find the optimal dimensions of the bucket in centimeters. Just a hint, 1 milliliter is roughly 1 centimeter cubed. So there's a volume component to that. And then we also give you your formulas right here for surface area and for volume. You'll want to pause the video here, give this one a try. I'll go over it in just a second. Okay, so the key idea behind these kind of questions are we have to try to get it so we're only dealing with two different variables. We got a lot of different variables here. We got surface area, we got radius, we've got height, we got the whole 9 yards. But the weird thing about this question is it only gave us the volume to begin with. So we really don't have a lot to work with to start. Let's just start there though. We know the volume is 12 liters. Now 12 liters doesn't really translate too well to like centimeters and stuff. So let's change 12 liters into milliliters. That would be 12,000 milliliters. And that actually translates quite well to a physical measurement. 12,000 milliliters is therefore roughly equivalent to 12,000 centimeters cubed. Maybe that's a better number to be using here. Anyway, so we can change that into our volume here. We'll say 12,000 is our volume, and that's going to equal pi r squared times h. Now, we really don't like having more than one variable on this one, right? So, you know, two variables is usually what I say though, just so we have like an area and all that. Anyway, long story short, what we want to do is we want to isolate one of our variables. I think the easiest variable to isolate here would be h. So let's divide by pi r squared on both sides. You know what, I'll just save myself the trouble and the space. I'm just going to divide by pi r squared. That's going to give me h equals 12,000 divided by pi r squared. No big deal, okay? Now, what we're trying to optimize here is the amount of material needed to make this bucket, right? Now, the amount of material is just another way of saying the surface area. The surface area of the bucket is just what the bucket is made out of, right? Now, this surface area formula, I've actually adjusted this for you. It's pi r squared plus 2 pi r h. That is the surface area of a cylinder that only has one end to it, right? So it's an open top bucket, as you would assume, you know, a bucket would be, you know, unless it had a lid, I guess, right? Anyway, so this surface area formula is all ready to go. Instead of saying SA, I'm just going to shorten that just to A. So the area of the bucket is pi r squared plus 2 pi r h. But just remember, h is another variable. We don't like using another variable. So how about we use what we established in the first place? And instead of h, I'm going to write in 12,000 divided by pi r squared. Now, before I do anything to this equation, you're going to notice something very helpful happens here. First of all, 2 is going to multiply by the 12,000. That's going to turn it into 24,000. No big deal there. But pi is going to cancel out with the pi on the bottom down there. So pi is gone. And this r here, when it gets multiplied on here, is going to cancel one of the r's on the bottom. So r here is gone, and we'll just knock that down to a single r. Long story short, this makes it a equals pi r squared plus 24,000, because of the 2 times 12,000, over r. Now, we want to optimize this. So we want to use the minimum amount of material possible. What that means is we want to basically make it so that we have a local minimum here. Now, a local minimum will come out of taking the derivative of this function. Don't get confused with when we were doing, you know, the rate of change of something over time. This bucket's not changing its dimensions. We're just trying to optimize it. So long story short, when we take the derivative of this area function, we are going to take it with respect to r. We're not taking it with respect to time or anything like we did in the other ones, because that would be, you know, a changing bucket. I would love to see that, a bucket that like literally expands over time or shrinks over time or whatever. That'd be pretty fascinating. But long story short, we're going to take this with respect to r. So if you take the derivative of this function, a prime is going to equal the derivative of pi r squared with respect to r is going to be 2 pi r, right? Because the squared just comes down. This one's a little trickier. Think of the r on the bottom as just being r to the power of -1. That's going to make this negative 24,000 over r squared. Or in other words, negative 24,000 times r to the -2. R to the -2, though, is just r squared on the bottom of a fraction, right? Anyway, we just need to solve for where this is minimized. In other words, we need to solve for where our derivative is equal to 0. So we just say 0 equals 2 pi r minus 24,000 over r squared. Let's bring this 24,000 thing all over to the other side. That's going to give us 24,000 over r squared equals 2 pi r. We can multiply our r squareds over here. It's a horrible looking r right there. There we go, a little bit better. Multiply our r squareds over, we have 24,000 equals 2 pi r cubed. We want to solve for r, so let's divide by 2 pi. My advice to you is divide each piece one at a time. Don't get carried away. Sometimes people get calculation errors if they try to do it all at once. So 24,000 divided by 2 and then divided by pi. I'll just write the number out here. That's going to give me 3,819.719, we'll say, equals r cubed. Long story short, let's just cube root this now. Cube root of that number equals, it doesn't say what I have to round to here. So you know what, I'm just going to round to the nearest tenth just to make our lives easier. 15.6, and I guess that's going to be in centimeters. So the radius of this bucket needs to be 15.6 centimeters. Now, if this was a question on a quiz or something, you would have almost full marks here. There's one more thing we got to find though. We're looking for the dimensions of the bucket. All we've stated so far is just the radius of the bucket. So we know what this part of that bucket is right now, right? The radius. We also need to know how tall this bucket is, right? Good news is we had a formula for height right over there. So just plug in 15.6 into that formula. Spare you the trouble of writing it all out. So 12,000 divided by, be careful, make sure when you put this in your calculator, put pi r squared in brackets just so you catch the whole thing. So pi times 15.6 squared. This is going to give me, oh, kind of funny. It's a good thing it's going to round. It's close to 15.6 once again, but it actually does round up to 15.7. So 15.7 centimeters would be that bucket. And here's what's kind of funny about that. If you were actually to visualize this means the radius of the bucket and the height of the bucket are almost the same thing. In other words, it's going to be a pretty elongated bucket. It's going to look something like that, basically, right? It won't be a bucket like what you see in this picture here. But anyway, that's neither here nor there. I'm not going to worry about that. Let's keep on going. I think we only have like one or two more questions here. Yeah. All right. So 2 baseball players are running to catch a fly ball. Tom is running east at 3 meters per second. Harry is running south at 2.5 meters per second. Find the rate at which the direct distance between the players is decreasing when we have this situation. Tom is 10 meters away from where the ball will land, and Harry is 7 meters away from where it'll land. And then we'll have a different situation in part B on the next slide. My advice, draw a picture on this one, guys. Draw a picture that's really accurate and all that. We'll go over this one in just a second. Okay, so drawing a picture here is going to do like everything the world of good here. Tom is running east. So we're going to say he's running east. East would be that way. He's running east at a rate of 3 meters per second. Harry is running south at 2.5 meters per second. Oops, maybe I should have drawn this arrow a little bit lower, I suppose. Maybe I should put that there. So there's Tom. Harry is running south. So Harry's running this way. I don't know how long these side lengths are. Well, I guess we do in the next part here, but whatever. I'm just going to draw it like that. The ball is going to land right here, we'll say. What we're looking for is the rate at which the direct distance between the players is decreasing. So the direct distance would be this hypotenuse piece right here. We'll call that D, distance. Now be careful on this question because it does say Tom is running east at 3 meters per second. That's not the X value here. That's your change in your X value. So in other words, that's how much your X value is changing per second. If X is the distance between like this way here and Y is the distance this way, then the change in your X would be the derivative of your X. So if we make like a data bank right here, we can say X prime is 3.0 meters per second. We know X is this distance here. Well, that's Tom. So he's going to be 10 meters away. So 10 meters is just our regular X. Y prime is the distance, or rather the rate of change of our distance right here. That's going to be 2.5 meters per second. And let's see here. We also know Y is going to be 7.0 meters because we know that's how far away Harry is from it. Now, before I continue here, some of you might have already noticed this. I just want to talk in terms of whether these rates of change are going to be positive or negative. I think as this guy is running towards the spot where the ball is going to land, I'll even just write ball right here. As this guy is running towards where the ball is going to land, and as this guy is running towards where the ball is going to land, the actual side length of this is actually shrinking, right? So in other words, he's getting closer and closer and closer to the ball. So the side length, X and Y, the distance he is from the ball, is shrinking. So what I think we actually need to do here, and I apologize for not mentioning it earlier, is these rates of change, the 3 meters per second and 2.5 meters per second, they actually need to be negative numbers. So I'm going to put a negative on both of those. And again, that's just because those side lengths are shrinking. It is the rate of change of our side length, or in other words, the rate of change of the distance that these guys are away from where that ball will land. I guess what we're looking for is the rate at which the direct distance between the players is decreasing. So what we're looking for is the rate of change of the distance. So we're looking for d prime. The good news is we can solve for d just by using Pythagoras here, right? So if we're wondering what d is, we can just use Pythagoras using our x and our y's. So 10 squared plus 7 squared equals d squared. That's 149 equals d squared. Give me a second, throw that in my calculator. 149, square root that is going to be d equals, I'll just write it over here, 12.2 meters. There we go. Okay, long story short, that was a whole big setup just to get all our information down. What obviously is a really important question to ask us is what is the relationship between these three values? We've kind of already done it to solve for the value of d. I was just doing that just to make a bank. But the relationship between these three sides is going to be x squared plus y squared equals d squared, right? Just classic Pythagoras here. I know some people were a little concerned from the last lesson. They were saying, well, how do I know, what formula to use and what? Well, the good news is if we have a right triangle and we're only dealing with the distances, like if the question mentions nothing about angles, you pretty much know you're using Pythagoras. It's just whenever you have an angle that things get a lot more confusing because then you have to use sine, cosine, tan, or sometimes even sine law or cosine law. Anyway, we won't worry about that right now. Since this is the expression that relates these three variables, and we're looking for the rate of change of our direct distance, that leaves us no choice but to take the derivative of this function with respect to time. So if we do this with respect to time, that's going to be implicitly taking the derivative of this all the way through. That's going to give you 2x times x prime plus 2y times y prime equals 2d times d prime. Good news is if you look at this crazy expression, we have all of the pieces of information except for d prime. So it's just a matter of throwing all of that information in. So this is going to give us, I'm going to just divide this away here, 2 times x, so 2 times 10 times x prime, which is negative 3.0. Watch that negative there, okay? Plus 2 times y, which is 7, times y prime, which is negative 2.5. Again, watching that negative there. Equals 2 times d, which is 12.2 times d prime. I think we all know you just got to add all these sides together. You know what? I'll just do it just out of whatever, right? So 2 times 10 times negative 3 plus 2 times 7 times negative 2.5. Oh, hold on. Sorry, I think I just goofed something up. Sorry about that. 2 times 10 times negative 3 plus 2 times 7 times negative 2.5. Yeah, I goofed when I put up my calculator. That's going to give you negative 95 equals 2 times 12.2. Well, that's just 24.4 times d prime. Divide by 24.4 on both sides. D prime is going to equal negative 3 doesn't say what we have to round to here. I guess I'll round to the nearest hundredth just for being exact. Negative 3.89. Negative 3.89, and I guess because that's a rate of change of the distance, that would be meters per second. So in other words, the distance between these two guys is getting closer and closer at a rate of negative 3.89 meters per second. Pretty cool. But again, part B is going to analyze whether that number, that d prime, stays the same regardless of how far away these guys are. So let's see this part B here now. So part B, it's the exact same question, except this time around, we're looking at when Tom is 4 meters away from where the ball will land, and Harry is 2 meters away from where it'll land. This one should go quicker. Pause the video here, give this one a try. So again, because it's pretty much the exact same context, let's just draw another picture. We're going to say that this is Tom heading east here, and this we'll say is Harry going south. And this, of course, is our distance between the two guys. Just like before, we know x prime, the rate of change of Tom, is negative 3.0 meters per second. This time around, though, x distance is actually only 4 meters, 4.0 meters. It's not as much as it was before. Likewise, we know y prime was negative 2.5 meters per second. And this time, what's changed is y is only 2.0 meters. D prime is still what we're looking for. We're looking for the rate of change of the direct distance. The value of d is also going to change because it's no longer dependent on those old x and y's. We now have 4 and 2 meters. So let's use Pythagoras to solve for that. That's going to be 4 squared plus 2 squared equals d squared. That would be 16 plus 4 equals d squared. So that'll be the square root of 20. Just give me a second. The square root of 20. We'll say d is equal to 4.47 meters. So just like before, what's connecting all of these variables together is the old classic Pythagoras here: x squared plus y squared equals d squared. That formula, of course, is no use to us anymore because we've just already used it for d. So let's take the derivative. That's 2x x prime plus 2y y prime equals 2d d prime. In case you're wondering, just by the way, I've never really done it for any of these questions. Since 2 is a factor of all of these, you could just divide both sides by 2 and you're good. You don't need to have all these 2's here. I'll leave it there just so it doesn't throw any of us. But whatever, you just so you're wondering, it's no big deal. Anyway, long story short, we have all this information. So just like before, let's plug these numbers in. I'm interested to see if d prime is different this time around. So in other words, if the rate of change of the distance between these guys has changed now that they're closer. No promises, no guarantees. Let's find out. So we're going to see 2 times x, which is 4, times x prime, which is -3, plus 2 times y, which is 2, times y prime, which is -2.5, equals 2 times d, which is 4.47, times d prime, which is what we're looking for. Let's add that whole left side together. So 2 times 4 times -3, plus 2 times 2 times -2.5. Oops, I goofed again. Look at me, I'm clumsy today with my calculator. Hold on, I'm just putting the wrong numbers in or something. Anyway, -34 is what I got. So -34 equals 2 times 4.47 times d prime. So divide by 2 on both sides and then divide by 4.47. And we got d prime equals to the nearest hundredth -3.80. And I guess that would be in meters per second. Let's have a look at that previous answer. It is, slightly different. It's not a lot different, just slightly different. And I would say that's not anything that we lost by rounding necessarily. At least I hope not. Interesting, nevertheless, though. Certainly very interesting. The answer is similar, but just a little bit off. Anyway, cool. Oh, well, hopefully that one went reasonably well. That's a concept from last class that we learned this, but it is what it is. Anyway, that's it. So it was a little bit of a long lesson today, but hopefully not too bad. For practice, please work on any remaining practice questions in your practice booklet. If you need any help, make sure you're reaching out and asking. Best of luck.